Right, today I'm going to talk about another problem of Rolfson. But some of this maybe will be used later for that previous problem of Rolfson as well. If two piecewise linear links are topologically isotopic, are they piecewise linearly isotopic? So Rolfson did not specify if these links are in the three-sphere or in some general three-dimensional manifold. It's actually ambiguous. From his paper, I will assume that it is about S3. In S3. Maybe he meant arbitrary three manifolds, but I cannot do that anyway. So I'm going to show that the answer is affirmative modulo certain conjecture about finite type invariance. And there are different versions of such conjectures, and today I'm going to prove a weaker theorem, and maybe next time, if it can be continued, I will tell us a stronger result. Okay. Well, maybe I should tell you some scheme, some implications. So, suppose that L and L prime are links in S3. Then we have the following implications. L and L prime are PL isotopic. This implies L and L prime are topologically isotopic. This implies, and this will be theorem 1, this was trivial. So theorem 1 says that this implies that for each n, L and L prime are n quasi isotopic. I will define very soon what this means. And then theorem 2 says that L and L prime are not separated by any finite type invariant which is well defined up to PL isotopic. So these are finite type invariants in the usual sense. There is also a stronger result about Kirk-Livingston or colored finite type invariants, and maybe I will get to it after the break. But before a break, I think this will be enough for us. And so, what does this tell us? Well, if you call this some conjecture, some interesting conjecture, conjecture X. So this is a sort of a version of Vasiliev conjecture for links modulo nodes. I will tell more details about this. I think it's a reasonable conjecture. So if you assume this conjecture, then all these rows can be reversed. And actually the converse is also true. If this conjecture is true, if and only if all these arrows can be reversed. And we state it. So theorem or corollary to theorems 1 and 2. Conjecture X is equivalent to the conjunction of, so let me call this arrow A, this arrow B, and this arrow C. Then this is equivalent to the conjunction of A, B, and C. In particular, X implies A. And A says that isotopic links are PL isotopic, which was Rolson's question.
Простите, вот в самом нижнем утверждении написано, что инварианты корректно определены, что это верно для инвариантов, которые корректно определены с точностью P или изотопии. Имеется в виду, что вот следствие состоит в том, что они инварианты, потому что если мы уже знаем, что они такие инварианты, то вроде из этого очевидно следует, что
Well, you see, the issue is that finite type invariants are usually defined just for links up to ambient isotopy. So when, of course, the word invariant can have different meanings, but if I am speaking about finite type invariants, then it's better to understand invariants as invariants of ambient isotopy. And then they don't have to be defined up to PL isotopy. In other words, if you add local nodes, they can change. But here I'm assuming that they don't change when you add local nodes. I'm only considering invariants which do not change under addition of local nodes. Yes, so finite type invariants I didn't define, I will define this later. So any questions so far?
Ну а что известно про эти инварианты, которые корректно определены с точностью до изотопии? Ну ничего не известно. Ну известны примеры, но описания этих инвариантов универсального нет.
This was the situation 20 years ago, but now something is known about such invariants. Namely,
Я имею в виду не инварианты конечного порядка, а вот именно...
Yes, I understand. Okay, if you don't like this statement, then I can tell you this. So assertion C, this arrow, is equivalent to the following. No, not C, X. X is equivalent to the following. L and L prime are ambient isotopic Yes. If, or you can say if and only if, they are not separated by any finite type invariants which are, or which is locally additive. What is locally additive? Locally additive means the following. So it is an invariant of links, and we I think we no, this is not needed. So the locally additive means the following. If I add to my link, take a connected sum with a local node, then this is the same as V of n plus V of this link which is obtained by taking this node and also a trivial link. So, I mean, put your node in some bool and then take trivial components. Means this. Okay? Is this definition okay?
В каком количестве берутся окружности или у них?
Well, this k lives on some component number I, and the other components are trivial. So I had some complicated link, and I'm taking the connected sum of the ith component with this node k. I can also take the connected sum of the other components with the trivial component, with the trivial link. It doesn't change anything. So, if you are familiar with Koncevich's integral, then I can say that L and so let me write Koncevich. So using his integral, the following can be proved. L and L prime are not separated by locally additive finite type invariants. Let me write here rational. If and only if L and L prime are not separated by any rational finite type invariance. Because you can just write the Kontsevich integral of the link and divide it by the Kontsevich integral of the components. So this Kontsevich integral takes values in a certain complicated algebra of chord diagrams, but it is an algebra, so you can actually make the division, and it is completed, so it's possible to make, yes, in algebra. Well, this is possible anyhow, and also it is additive. It is the well-known result that the Kontsevich integral is additive under such connected sum. So, if you have any, so this thing will be invariant under addition of local nodes. Actually, it's not just locally additive, but even well defined up to PL isotopy. So by using this fraction, you can prove this easily. But this is only for rational finite type invariants, because in this algebra there are rational coefficients. But nobody knows if there exist finite type invariants which are not functions of rational finite type invariants. And also, if you don't like this rational, then I can erase this, but I can add, but here this will be string links. And this is what I hope to prove next time, not today. Does this answer your question, Petr Mikhailovich?
Ну, в принципе, да, но мне понятно, что тут сложный материал, но, в общем, я не очень это самое, не очень понял ответ, но формально все ясно. Давайте дальше.
I will tell this in more detail gradually. Let us discuss simple things. So I erase. Oh, can I erase everything? Okay, so I want to define n quasi-isotopy. And also strong n quasi-isotopy. So, let me consider the disjoint union of circles. This is the first one and the nth one. And I want to map it to a, okay, this can be a three-manifold. So this map F will be a piecewise linear map with precisely one double point. So F is called a strong and quasi embedding if there exist arcs J0 and so on J and in M+1 and three-dimensional balls B1 and so on Bn in S in our manifold M3 also, so this double point has the following form: f of p equals f of q, and we can also call this x. So p is not equal to q. And then want b0 to be just this point x. This will be balls and b0 will consist of just one point. Or you can take a very small ball around it. Such that the following two conditions hold. So if I take the inverse image of Bi, this lies in Ji. Okay, so this should be for I less or equal than n. And if I look at the image, well, okay, I can write Bi union the image of Ji, then this should be contained in Bi+1. Okay, this is the definition. And a strong and quasi isotopy is a homotopy through embeddings and through strong and quasi embeddings. I will return to this definition in a moment.
Есть вопрос.
Что такое тау-и?
Ji is an arc.
Ну а что такое арк? Вот это
дуга. Let me draw some pictures. Let us consider the case n equals 0. Okay, what does it say when n is equal to 0? So there must exist one arc J0 and nothing about these balls. But we have B0. So
Но это дуга с концами в точке X? Или не обязательно?
yes, it can be. Let me say. So this says that f inverse of x lies in J0. And we don't, okay, this for I less than n. We don't have this condition because n equals 0. So the only condition that we have is this, namely that our this is the same as saying that P and Q lie in J0. The only condition is that these 2 points P and Q lie in some arc. This means that they lie in the same component, and it doesn't mean anything else. So we are allowed to make self-intersections, and we are not allowed to intersect distinct components, and that's all. So zero quasi-isotopy. Okay, it was strong. Zero quasi-isotopy is the same as link homotopy. Okay, what about n equals 1? Now we have also J1 and B1. And so which conditions do we have? We still have this condition. Then we have now this condition B0 union f of J0 lies in B1. Okay, this is interesting. So B0 is our point X, and J0, okay, this. So we have this self-intersection point, and so yes, so this is a map. This is X, and it has two preimages P and Q, and well, we have to select either this half or that half. This arc will be either like this or like that. So, for example, I select this, and then its image is like this. Then this says that this loop must lie inside some ball, B1. Okay, what do we know about this B1? Well, I think we only have this condition for B1, namely f inverse of B1 lies in J1. But there are no other conditions about J1. So actually this condition says that this ball intersects our link so that this intersection lies in an arc. It has to be a bigger arc than this one because this one is already contained in this ball. But we are allowed to have some additional parts of our link inside of which, for example, like this. And then then we can choose. So this orange one was J0, and now I want to draw J1. It can be like this. So in this picture we have one quasi-embedding, but what is the condition? What are we not allowed to have? Well, we are not allowed to have any piece of another component inside of this ball.
Один надо немножко побольше нарисовать, чтобы синенькие поместились.
No, this green.
Не обязательно совпадает.
This green one doesn't have to be contained inside of B1. The preimage of B1 has to be contained in J1. See this preimage.
Там тогда зеленую верхнюю чуть-чуть продлить надо.
Okay, I can do that. Yes, this can be longer. I don't. Yes. Yes, you're right. Actually, yes, okay, it was right. This could be J0, and then this one must be longer because this is the ball. Yes, thank you. So we are not allowed to have any part of another component inside of this ball.
Но всегда же один такая существует, потому что мы можем взять почти что полный компонент, который содержит пику, чуть-чуть там до точки дойти.
Yes,
если это не поглотит всю компоненту, тогда существует.
Yes, this is one problem, that this ball can cover all of this component, but this is not a big problem because you can always push a small piece out of it. But there is another problem. If you have another component, a second component, which intersects this ball, then you will have a problem because the preimage of this ball has to be contained in an arc. And if you take some point from another component, you cannot have an arc. So this is prohibited. So strong one quasi-isotopy can be reformulated as follows. We're allowed to have self-intersections of components such that at least one of the two resulting lobes. Okay, so by the lobes I mean these two loops. This is the terminology of Kirk and Livingston. I don't know how to say it otherwise. In Russian maybe половинки, ушки, восьмерки. The two loops which the two loops into which this intersection point splits the component. So at least one of them lies in a three ball which is disjoint from the other components. Of the link. So what happens when n equals 2? Or any questions about n equals 1?
Есть вопрос. Self-intersections во множественном числе написано просто потому, что на каждом шаге гомотопия?
Yes, because we have a homotopy which can have several self-intersections, but at each. So I didn't try it. So quasi-isotopy is homotopy through embeddings and strong and quasi-embeddings. So we can have several strong and quasi-embeddings in such homotopy.
Если, во-первых, вопрос по-русски это дословно все сильно n квазиложение.
Да?
Вот не сильно это что?
I didn't define yet. I will come to this. But let us look at the case n equals 2. Or maybe I just draw a picture.
Еще маленький вопрос. Здесь про самопересечение написано так, как будто они многие могут быть одновременно. Имеется в виду, что всегда можно развести? Или все-таки...
Well, okay. One, at most one, at each time instant. Okay. Okay, so what happens when n equals 2? Let me still go to this definition. So we have another condition. Now B1 union f of J1 lies in B2. So the union of this orange ball and this green arc must be contained in some new ball. And this, okay, so what are we required of this new ball? Well, the same as before. F inverse of B2 lies in J2, and J2 must be an arc. So this new ball cannot intersect other components in particular. Well, this is essentially all. This is all. It can intersect these components with our component any way it wishes, because even if all of it lies inside of this ball, we can push a little piece out of this ball. So really the requirement is that the other components are disjoint from this ball. So let me draw a picture of a link which is...
Сейчас, я не понял. Значит, вот есть гомотопия, а вы говорите, что эти гомотопии теперь еще должны удовлетворять новым свойствам. Эти свойства, они что, сильнее? Что еще? Из 1 квазиизотопии 0 квазиизотопия следует.
So n quasi-isotopy implies n minus 1 quasi-isotopy always. N minus 1. Because we just add more conditions. Okay? So, first I can just draw the Whitehead link. So the Whitehead link is, of course, zero quasi-isotopic to the trivial link.
Так, а Тау-2, оно стало быть, какой шар? B2 маленький, B1 маленький, B2 побольше, да?
Yes, this was B2.
То есть обязательно получается, что G2 расширение Тау-2, расширение Тау-1.
Yes, J2 must be a bigger arc, which contains a preimage of B2, J2, so it can be like this. All right, so if you just make the self-intersection here, you will get a link homotopia, which is a zero quasi-isotopy. But this is not going to be a one quasi-isotopy. We don't get a one quasi-isotopy. Because when we do this self-intersection, let me draw it. Well, we have these two loops now. Let me, for example, pick this loop. So we are required now that this loop be contained in some ball which is disjoint from the other component. But as you can see from the picture, there is no such ball. So this is not a one quasi-isotopy. And in fact it can be proved that the Whitehead link is not one quasi-isotopic to the trivial link by using the Sato-Levin invariant. Okay, so next picture. The next picture is this Milner's link, and this one is one quasi-isotopic to the trivial link, because I can make the self-intersection here, and I will obtain the following picture. Here I can choose, so we get these two lobes, and I am choosing this lobe. I can choose any one I like. So here I had to look also at this lobe, but they are similar, no much difference. And here I'm choosing this one, so I'm free to have a choice, because at least one I can choose. And it does lie in this ball, which is disjoint from the other component. But this is not going to be a two quasi-isotopy. Because if I want to construct the second arc, well, it has to contain the first arc. So it has to go like this, I think. It has to contain the preimage of the entire ball. So it has to be like this. Okay, but also this would be good, but also it has to contain this part. But then, if I wanted this to be an arc, then I have to close it either here or here. But in any case, if I want to draw the next ball, which contains this green arc, I cannot do it. The next ball will intersect the second component. And actually, it can be proved that this link is not quasi-isotopic to the trivial link by using the second coherence invariant. And you can draw a series of such links. These are Milner's links, Mn. So this is the Whitehead link was M1, and this is M2, and then there is M3. So Mn is n-1 quasi-isotopic, but not n quasi-isotopic to the trivial link, to that link. And this is not just a conjecture, it's a theory. It's proved by using Cochrane's invariant. Questions? Now let me define n quasi-isotopy without strong. So I will just modify this definition cross out strong. So still I need these arcs, and instead of the balls I will need compact polyhedra. So let me now call them P1 through Pn, because these are not balls but just polyhedra. Also P0 is the point. Such that, same condition here, the preimage of Pi lies in Ji for I less or equal than n, and the union of Pi and f of Ji lies in Pi plus 1, same condition for I less than n, and moreover this inclusion, this one, is null homotopic. So this union is null homotopic inside of Pi plus 1. I'm not requiring them to be balls anymore, but I just want these unions to be null homotopic in the next one. So, zero quasi-isotopy will again be the same as link homotopy, because nothing is really changed here. And one quasi-isotopy will be equivalent to the following. We are allowed to make self-intersections, at most one at each time instant, or self-intersections of components, such that at least one of the two resulting lobes is null homotopic in the complement to the other components.
Это не то же самое.
Yes, this is equivalent to one quasi-isotopy.
Я имею в виду,
Do you mean is strong one quasi-isotopy as equivalent to one quasi-isotopy? I think no, but I don't have a proof. So and here is why I think that they are not equivalent.
если стягивается, то есть диск, его можно превратить в несамопересекающийся диск вроде, а у него есть такая шар, или несамопересекающийся это только в трехмерной сфере.
Let me draw a picture. So this is the second whitehead link. Whitehead 2. So if I make the self-intersection here, this will be one quasi-isotopy, or maybe I should say this will be a one quasi-embedding, and we will obtain a one quasi-isotopic to the unlink. But this will not be a strong one quasi-isotopic. So let us look at what happens. Let me just draw it here. So I have to choose one of the two loops, but in this case they are not very different. So let me choose this one, for example. So this one is null homotopic in the complement to the other component, but it is not contained in any ball in the complement to the other component. But this is a two. Yes, so this is a one quasi-isotope, but not a strong one quasi-isotope. Yes. And you can also construct iterated whitehead links, whitehead n, which is n quasi-isotopic to the unlink. Just by inserting more and more of such whitehead curves in the solid tori. But it seems that it is not strongly one quasi-isotopic to the unlink. And also it seems that it is not n-1 quasi-isotopic to the unlink. But these assertions are not proved. Question mark here and question mark here. These are conjectures, and so these are maybe you can prove them. I suspect that this can be proved by using the Jones polynomial. But I don't know. I didn't check it. This cannot be proved by the Alexander polynomial. No way. And for strong one quasi-isotopy, I don't know how to construct an environment here. It looks from the picture, it seems to be clear. But I don't know what is the environment. How to prove this. Okay, theorem. Any questions? Theorem. So this is theorem 1, or a stronger version of theorem 1, which I stated before. So let ht from ms1 into the 3 manifold M be an isotopic. Then, for each epsilon greater than 0, for each n, there exists an epsilon greater than 0, such that any generic piecewise linear homotopy epsilon close to ht is a strong and quasi-isotopic. So this is an old theorem. It was published 20 years ago, but I wrote down the proof only for the case n equals 1 in the published paper. And today I wrote down the proof for all n, and I want to tell you this proof. There is nothing complicated. It is almost obvious, but because many results are now based on this theorem, I think it makes sense to study the proof in some detail. So first of all, I will need a lemma. Yes, so before lemma, I should say that I'm going to use a metric on the manifold such that epsilon balls are piecewise linear balls in this metric. For example, if M is the Euclidean space and you use the L infinity metric, then the balls are going to be squares or cubes, and they are piecewise linear. But if you use the Euclidean metric, they are not piecewise linear. And the lemma says that for each delta greater than 0, there exists a gamma, which is a function of delta, also greater than 0. Well, this all depends on n, on ht, so ht is given. Such that for any triple E U T in MS1, times ms1 times I such that the distance between P and Q is less or equal than gamma. The following holds: P and Q belong to the same circle and are not antipodal. And are not antipodal in it. And the HT image of the shortest arc PQ. So since they are not antipodal, we can connect them by geodesic, so to say, in the circle. And I call it PQ. So this image is of diameter less than delta. So it says, well, we have our HT. Maybe I just draw it for a fixed t, HT0. And then we look at 2 points. So HT, it is an embedding, it is injective. So the images of these 2 points are always distinct. But then I should be able to connect these 2 points by an arc such that the image of this arc is not too large. It can be bigger than the distance between these 2 points, but it has to be only slightly bigger. It has to be bigger in a controlled sense.
Ну, это один квазиизотопия примерно.
Yes, but actually this lemma will be enough to prove the theorem for all lemma. So how to prove this lemma?
Повторите то, что вы говорили, когда вводили вот сейчас на дугу.
So there cannot be
было ли там что-то, кроме вот дословно этой же леммы?
No, it's just an informal way of stating this lemma. So this, if 2 points are sufficiently close, then they are always connected by an arc whose image is small enough.
То есть, если точки гамма близки в многообразии, то между ними есть путь длины диаметра не больше delta.
Yes. So, for example, if gamma of delta is a linear function such as gamma is k times delta, then this arc can have diameter just k times greater than this distance. So to prove this lemma. So let V delta be the following subset of ms1 times ms1 times I. So it will consist.
Тут в значении гомотопии в этой лемме нету. PQT принадлежит, это прообраз MS1.
So HT is used here.
Ну хорошо, ладно, есть.
So this will be the set of all P, Q, T, just like here. P and Q belong to the same S1I, are not antipodal in it, and HT of this shortest arc PQ is of diameter less than delta. So because I put here less, strictly less, this V delta is going to be open.
Простите, вот там написано расстояние между P и Q не больше гамма. Какое расстояние имеется в виду, если тригонометопия меняется? Имеется в виду внутреннее расстояние на окружность?
Yes.
Значит, до отражения какое-то другое.
Yes, this is a very good point. This is the distance between HT of P and HT of Q. Thank you.
А это для любого-то?
We have one T here. So this is a homotopy, so we cannot take P and Q from different levels. It doesn't make sense to take them from different levels.
В чем тогда, то есть написано of the shortest arc, это имеется в виду, что здесь T выбирается какой-то...
This is the same T.
Одна из двух имеется в виду, the shortest это одна из двух, да?
Well, it is. I wanted to be determined. So it is. I consider some metric on the circle, and this is a geodesic arc. So it's the shortest. So there are always two arcs, and it can happen that they have the same lengths, but this happens only when these 2 points are antipodal. So if they are not antipodal, there is a standard arc, there is no choice.
Вот это утверждение про то, что они противоположны, оно разве нужно, если мы уже знаем, что расстояние вот то очень маленькое? То есть ясно, что можно выбрать такую гамму, что все противоположные точки на расстоянии больше, чем гамма. И тогда это условие про менять туда не нужно.
Well, I don't know what number is gamma.
Но зависит, оно существует. Тогда его можно выбрать таким, чтобы все антиподальные находились на больших расстояниях. Тогда не нужно тащиться с точки антиподальной.
Yes, but this is I have to state it somehow. If I don't write here that they are not antipodal, then there is a question: what is the shortest arc? So.
Ладно.
Вы, по-моему, 2 раза одно и то же написали. В этой лемме уже написано. Еще теперь приписали справа.
Yes, this is the same, but this is the definition of the set V delta. And this will be an open set because this inequality is strict. If I shift these points PQ and also T, if I shift them a little bit, they are not going to go out of this set. They are not going to become antipodal if they were not antipodal, because again this is an open condition. And so this is an open set. And if I consider the complement m as 1 squared times I minus V delta, then this complement is compact. It is closed and this thing is compact, so it is compact. And if I look at its image under HT, it is also compact. The image of a compact set is compact. Then, and also it is, so it is compact, and also it is disjoint from the diagonal. Well, okay, I think. Yes, this is some different map. So H is a map from m as 1 squared times I into m3 squared. m3 times m3. Define it in the obvious way. So P Q T goes to HT of P and HT of Q. But HT is an embedding. So if P and Q are distinct, then these 2 points are distinct, so we do not hit the diagonal. Disjoint from the diagonal of M3, which lies in M3 times M3. Also, this set is compact, so there is a non-zero distance from this set to this diagonal. So there exists, actually I think this is our gamma. Yes, such that if distance between 2 points x and y is less or equal than gamma, then this pair x y does not belong to the image to this. Let me call it z. Because this z is compact and it is disjoint from the diagonal. So there exists a gamma neighborhood of the diagonal which is still disjoint from z. And this is what we want, because now if we find points P and Q such that the distance between their images is less or equal than gamma, then they will go into this neighborhood which is disjoint from this. But on the other hand, yes, so this triple will not be in this set V delta. No.
Дополнение, значит, будет...
Yes, yes. This was the complement. This was the complement. So they don't belong to the complement of V delta, so it belongs to V delta. So this condition holds and then is proved. Okay? So now let us prove the theorem. Well, I don't know what I can erase. Can erase this. Can erase this. So now I'm proving this theorem. For each n there exists an epsilon. I'm given an n and I want to define the epsilon. This is how I define the epsilon. First, epsilon n plus 1 is arbitrary positive real number. Any number you like. And then epsilon I is defined using the lemma. This will be 1/2 of gamma of epsilon I plus 1 over 2. So essentially I'm just applying this lemma n times, or n plus 1 times, to any given number. And in the end, epsilon will be epsilon 0. Now, here I want to construct the balls. So let me return the balls back. And I don't need this moreover. No. So what are going to be the balls? So Bn is well, I think I missed something. Yes. Yes, so this is how I define the epsilon. Then I'm given a generic PL homotopy, epsilon close to HT. The epsilon is y and the homotopy is given by somebody. Then this homotopy has only finitely many double points, and because it is generic, these double points occur at different time instances. Let us pick one of these moments, and so we have our HT. HT we were given. But this generic homotopy, we need some different letter for it. Let's call it FT. And we have some singular moments, T1, Tn. Now we pick one of them, any one, and just look at this moment, because we want to prove that this Fti is an n quasi-embedding. So we want to prove that this is an n quasi-embedding. And so let me call it just F. We can forget about this other moments now, and also I can call H. H can be used for HTI. So now I have the following picture. I have some moment of this topological isotopia, and I have a not such a good picture. So there is this topological isotopia, and this is H, which is HTI, some singular moment. And then I have a piecewise linear approximation which actually has a double plot. So this is F, which is FTI. And I want to prove that this FTI is an n quasi-isotopy. So now I have this point, this double point X, which is f of p and also f of q. And also, so B0 will be this X as we have in the definition, and Bn will be the ball of radius epsilon n. No, Bi I should say, Bi, ball of radius epsilon I about this point X. So I'm just taking balls about this point of larger and larger radiuses. But actually in this picture I think I should draw them like this. They are small enough in this picture. They will not be bigger than this distance, I think. Okay, so it remains to prove these inclusions. To construct, yes, I also want to construct these arcs Ji and to prove these inclusions. So first, I need to construct the arc J0. Well, of course, J0 will be the shortest arc PQ. So then, we want to show that its image lies, yes, so we already know that each ball lies in the next ball. This doesn't need to be proved, this comes by definition. Of course, each epsilon I is less than epsilon I plus 1, and actually you can even write that it is less or equal than epsilon I plus 1 divided over 4, because you have 2 and 2 here, and gamma it cannot increase. So in this lemma, gamma cannot be bigger than delta, because this image of the shortest arc, it includes these 2 points. So we have this inequality. So now yes, we have this inclusion, and we want to prove this inclusion. F of J0 lies in B1.
Гамма, что такое, извините?
Gamma is a number given by the lemma. So actually it's a function, gamma of delta. And here I'm using this function. I'm applying it many times.
Ясно.
So
Но это свойством непрерывности гамма, что-нибудь надо воспользоваться или никак? Все, что любая функция гамма может быть.
no, I don't need gamma to be continuous. It can be discontinuous.
Но она все-таки маленькая должна быть, если дельта маленькая.
Yes, yes.
А где это написано?
Well, gamma cannot be greater than delta because this image of this shortest arc contains these 2 points. Here, this pink arc contains these 2 points. So it cannot be, okay. This distance is delta, and this diameter is this distance is gamma, and this diameter is delta. Okay, so here this x is the image of P and the image of Q. But I can also look at their images under my original isotopy. So this is H of P and H of Q. And they're not far from, so this was an approximation of the isotopy. So this distance is at most epsilon, and this distance is at most epsilon. I'm given a generic PL homotopy which is epsilon close to my isotopy. So the distance between these 2 points is no more than 2 epsilon. But what is 2 epsilon? 2 epsilon is the same as 2 epsilon 0, because epsilon is the same as epsilon 0. And 2 epsilon 0 is gamma of epsilon 1 over 2. So now I can apply this lemma to these 2 points. So they satisfy this condition, and then it means that this arc, has diameter less than gamma, less than delta, or in our case it has diameter less than this number. So this diameter will be less than epsilon 1 over 2. But I'm more interested in the diameter of this pink arc. Well, in this picture it is even less than this, but of course this pink arc can go like this. But here the distance is again epsilon, and here the distance is epsilon. And if I add epsilon 1 over 2 plus epsilon and plus epsilon, well, we have epsilon is the same as epsilon 0, and it is less or equal than epsilon 1 over 4. We have this inequality here. So the sum is less or equal than epsilon 1. So this diameter of this pink arc is less or equal than epsilon 1. And this means that this pink arc lies inside of B1. Because B1 was the ball of radius epsilon 1 about x. And every point of this arc is at distance no more than epsilon 1 from x. So for n equals 1, we are done already. So let me do the case n equals 2, and then the other cases are similar to n equals 2. Well, actually, the case n equals 2 is also not much different. So I want to construct the arc J1 now. J0 was just this shortest arc PQ, but J1 has to be constructed. So how do I construct J1? Well, I have this ball B1. Let me draw it with some other color. B1. So let me take some point R which lies inside of B1. Or maybe this is F of R. So it lies on the image of F, so it can be here or here or here, but inside of B1. And I want to compare it with this point. Or more precisely, I have 2 points here, P and Q. I want to compare it with Q. Well, anyway, first I look at this distance. The distance from F of R to this X. This distance is less than epsilon 1, because this was a ball of radius epsilon 1. So this distance is less than epsilon 1. Well, I also have this point here. So I have h of r and I have this h of p. This distance is less than epsilon, and this distance is also less than epsilon. So the distance between these 2 points is less than epsilon 1 plus epsilon plus epsilon. So this will be less or equal than to epsilon 1, because epsilon is epsilon 0, which is which is less or equal than 1 than epsilon 1 over 4.
Почему эпсилон, вот первое слово эпсилон 1, почему это верно? Что h от r, h от v?
So this distance between f of r and x is less than epsilon 1, because I just take this point to be contained inside this ball B1, and it has radius epsilon 1. So this distance is less than 2 epsilon 1, and then again I have just like I had here 2 epsilon 1 equals gamma of epsilon 2 over 2, and then I can apply this lemma to this arc, starting from this point and ending at this point. So this arc. And this lemma tells me that the diameter of this arc is less than delta in these terms, or here it will be less than epsilon 2 over 2. So the diameter of this arc, and draw it like this, less than epsilon 2 over 2. But I'm more interested in the diameter of this arc, starting from this point and going here until it comes to x. And again, like we had before, because the distance between
Сергей Александрович, вы пишете, что последний эпсилон произвольный. Это разве так можно дописать? Вон у вас там написано.
Yes, good question. I was surprised that I can choose this arbitrarily. First, I thought that this epsilon has to be chosen as the minimal distance between different components. But минимальное расстояние между разными компонентами. But actually, it turns out that this is not necessary. And but you see, here is n plus 1. I need only n quasi-isotopia. So this is an extra step.
Ну ладно, в общем, вы так написали, что это самое, вам не нужно.
Дополнительный шаг. Я применяю эту лемму больше, чем надо, дополнительный раз. I'm applying this lemma one more time than I would need normally. And this is why I start with arbitrary epsilon. So epsilon n, this is arbitrary, but epsilon n is not arbitrary, and I really need this one. Okay, so here the diameter of this white arc was less than epsilon 2 over 2. Epsilon 2 over 2. And then I'm adding the distance between pink and white, which is epsilon, and I'm adding it again, and this will be less or equal than epsilon 2, because again epsilon is the same as epsilon 0, which is less or equal than epsilon 1 over 4, and also less or equal than epsilon 2 over 4. So this means that the diameter of this pink arc is less than epsilon 2. And this means, well, the picture is not very good, but the point is that this point was inside the orange ball, but this arc, it doesn't have to be inside of the orange ball, it can go outside like this. But I proved that the diameter of this arc is less than epsilon 2. So, and this arc contains the point x. So this arc must be contained in the ball B2, which has radius epsilon 2. Now, well, I now have many such arcs, and all of them start with x and end with some arbitrary point lying inside the first ball. And all of these arcs lie inside the second ball. Well, I can simply take the union of all of these arcs, and this union will be still inside of the second ball. And this union has to be connected, because all of these arcs have a common endpoint. So it is a subset of a circle which is connected, and also it does not contain, none of these arcs contains the point which is antipodal to P. So somewhere we have the point minus P, which is antipodal to P on the circle. But none of these arcs can contain this point, because we are applying this lemma to these arcs, and this lemma says that they are not antipodal. So then the union of these arcs must be an arc. Because it is not the whole circle, it doesn't contain this point. It is connected and it is compact. Yes. Well, it is compact because because this ball was compact, and there is this largest arc somehow, so it has to be compact. This is piecewise linear, so it's not a big deal. So then I obtain this arc J1. So J1 this was J0, and J1 will be the union of all these shortest arcs from P to R over all R. Well, R is contained in B1 and also in the image of F. And this J1 is an arc, and it lies inside the second ball. So I think I completed the second step, and I proved this theorem for n equals 2. And the third step is completely similar to this. I'm just taking any point which lies on this image of F and lies inside of this second ball, and then I proceed in the same way. And in the end, let us discuss what happens in the end. So in the end, I will have this ball Bn plus 1 of arbitrary radius. But I don't need this ball. This strange ball Bn plus 1, it can be very large. It can contain everything, but it is not needed, because we need only strong n quasi-isotopy. But the important thing that we get is the arc Jn. And to get the arc Jn, we use the last application of this lemma, which needs also, well, which lands in this ball B1. And so this last step gives a construction of the arc Jn in the same way as the union of such arcs of the form PR. And this is going to be an arc by the same argument, and this is what we need for the definition of strong n quasi-isotopy. Any questions about this proof?
Получается не общая, получается вот общность там только в том смысле, что в каждый момент не более одного самопересечения.
Yes. Generic, well, I didn't say exactly what generic means, but yes, you can define it just like this, that at each moment you have at most one self-intersection. Yes, you can define it in this way.
Изотопия это гомотопия в классе вложений. Изотопия это гомотопия в классе вложений.
Well, I don't know how good what idea was to spend such a long time on this theorem. It is not difficult. It is not some deep theorem, but I don't know. It is used in all other results. So I think we have checked it. It seems. Maybe it's time to make a break. Unfortunately, so the theorem 2, which I hoped I would prove before the break, will have to be discussed after the break. Okay, so let me continue. So I want to tell about finite type invariants. And how they are related to n quasi-isotopy. But first I have to recall the definitions. So suppose we have an environment of links. So up to ambient isotopy. So we if we consider the space of links, it can be understood as a map from the space of links into some abelian group. We have to assume that this group is abelian. Maybe actually, I think it would be interesting to develop the theory of finite type invariance with values in nilpotent groups. Petr Mikhailovich, have you seen such approach?
У меня нет идеи. Ну, наверное.
But
Можно что-то.
I haven't seen any.
Ну, наверное, классики уже обсудили этот вопрос. Видимо, там известно, что можно там с этой теорией сделать. Пусть будет как положено.
Yes, everyone considers abelian groups here. It's clear why. It's clear that this is used, but it is not clear why they didn't try to generalize it, because it seems to be natural. Okay, so now we consider a bigger space, a space of singular, singular links. So singular links are just piecewise linear maps with a finite number of double points. So we fix actually the number of components. We have this MS1, which is the disjoint union of M circles, and we consider PL maps from MS1 to over 3 manifold with finitely many double points. And no triple points. So this V will be extended to V bar, defined on the space of singular links with values in the same group. And this V bar is defined by the following formula. So if we have a self-intersection point, then it can be resolved in two ways. Actually, I can just write it here. Well, first this can also be called V bar, so V bar restricted to embedded links is just V. So here I can write V bar, and now I draw the two resolutions, and I can never remember which one is plus and which one is positive and which is negative. Oh, no, I cannot draw it here. Petr Mikhailovich, is this correct? or
Да, верхнюю вращаем в положительном направлении.
This is positive.
Да.
Very good.
Положительное направление считается против часовой стрелки?
Ну да, ну так считается, что.
Well, this picture is not as a drawing. It is a picture not about links, but about plane diagrams of links. But actually, this definition is not just for diagrams, but for links, because of the following. So how to determine that this is positive and this is negative? Without drawing a plane diagram. How to determine it in the three-dimensional space? So you just have some double point in the three-dimensional space. You don't have any diagram on the plane. And how to determine which resolution is positive and which is negative? Well, let us look at some resolution, and we have these 2 points whose images will be the same here. We can draw a vector from the first point to the second. Actually, there is no reason why this point is first and this point is second. But temporarily, let us call it first and this one second. Then there is a vector from the first to the second, and also there are orientations here and here. And we obtain a frame. And it can be positive or negative. So what happens if we exchange? What happens if this point is the first one and this point is the second one? Well, okay, let me go back. This was first, this was second, this was V1, this was V2, and this was V12 maybe. So V1, V2 and V12. And now I exchange them. Then the picture will, this frame will change as follows. V1 will become V2 because I rename 1 into 2 and 2 into 1. This V2 will be renamed into V1. And this V12 will change the sign actually. Because 1 and 2 changed and this vector looked from 1 to 2. So this will be minus. Well, I don't know. This can be called V prime 1, 2. Yes. And it is minus V1, 2. So these two vectors exchanged, and this one changed the direction. And the sign of the frame didn't change. Okay, so according to this formula, we can extend our invariant from embedded links to singular links just by looking at any double point and resolving it in 2 ways. So there can be more double points in this picture, then there are more double points also in these pictures. But assuming that we extended our invariant to links with fewer double points, we can use this extension and do it inductively. And it doesn't matter in which order you resolve these double points, the result will be the same. Now, V is called an invariant of type n. If V bar vanishes on all singular links with more than n double points. And a finite type invariant is an invariant which is of type n for some finite n. So, examples. So, what is a type 0 invariant? Type 0 invariant must vanish on all singular links. If it has at least one double point, then it must vanish. So, for embedded links, we have that such difference is always 0, which means that we can make crossing changes in any way we like. So, type 0 invariant is a constant, which it's an invariant which assumes the same value on all links. What is a type 1 invariant? It is an invariant whose extension vanishes on singular links with two double points. So, if you have one double point here, somewhere, then when you add a new double point, this must be 0. And so you can make such crossings whenever you have already a double point. And so the value of this v bar on singular links with one double point doesn't depend on anything except the combinatorics of this double point. And it can be different actually. It can be a self-intersection of some component, or it can be an intersection of different components. Well, the linking number is actually a type 1 invariant. And indeed, if you consider intersection between distinct components, you can put always 1 here. And then this means that whenever you pass through such crossing, the linking number will change by 1. In which direction it will change is determined by these orientations, and I'm not able to describe this now. So, what is an example of a type 2 invariant? Well, for example, we have the Conway polynomial of a knot. It has the form 1 plus c times z squared plus something times z to the 4th. And this c is also called the Casson invariant. Now, for the Conway polynomial, we actually have a very similar formula. A nabla of the positive resolution of z minus nabla of the negative resolution of z equals z times nabla of the smoothing. So it's just like this, but here I replace this picture with the double point by this picture with the smoothing, and also I add the multiple of z. Now, if you look at a two-component link, then its Conway polynomial is of the following form. The linking number times z plus something times z cubed. So actually you can see that the linking number is of type 1 also from this formula. The linking number of this thing minus the linking number of the negative resolution is going to be, well, we have to consider the smoothing, and if this is an intersection between distinct components, then this smoothing will be actually a knot. You can see in this picture, if you do the smoothing, then it becomes just one component. And here this linking number is a coefficient at z. So and we multiply by z here. So here we have to take the coefficient, the free term, and the free term is 1. So actually it is 1 which doesn't depend on anything. This is just what we had. But now we can do the same with this c. So c of the positive picture minus c of the negative picture must be equal by this formula to the linking number of the smooth picture. So here we have this was a knot. C was an invariant of knots, and when you have a self-intersection of a knot and you smooth it, you can see that you will always get two components, and so this is the linking number of this two component link. Okay, but on the other hand, we have this formula. So this can also be called C bar of the picture with one double point. And then, if you go back to this picture, well, if you had some smoothing somewhere here, then you can write the same formula with C bar and here has to be yes, this has to be 1. So actually it's just 1, it doesn't depend on anything. And so this means that this C bar well, it can be also called C bar again of this link with two double points. Or maybe I should write it on this side. But anyway. But this equals 1, so actually this C bar equals 1. And so when we have 3 double points, this C bar will be 0. So this C is a type 2 invariant. So in the same way, you can see that in the Conway polynomial, if you take a coefficient at z to the power n, you will get a type n invariant. You can check it, it's easy. Any questions? Maybe it's too little examples, but we also have not much time, so I think I should try to continue. So theorem 2, if L is n quasi-isotopic to L prime, yes, so this can actually be in any 3 manifold. I don't use S3 anywhere. So okay. Then okay, and V is a type n invariant well defined up to PL isotopic. And then V of L equals V of L prime. Okay, proof. So actually this is also true for finite type invariants in the sense of Kirk and Livingston. This is a stronger theorem, but maybe I first prove it and after that explain this Kirk-Livingston invariance. So we can assume that it is an elementary and quasi-isotopy. So we have just one crossing change. This is L. This is L prime. And this is X. A singular link which is n quasi-embedding. We may assume that there is just one. We have to consider just one n quasi-embedding. Yes, let's consider the case n equals 1. So in this case, this must be a self-intersection of some component, and there must be one of the two loops which is null homotopic in the complement to the other components. I can modify this null homotopy a little bit so that it becomes a homotopy from this X to a singular link of this form, which is is the same. The other lobe is the same, and instead of this lobe, we have a very small loop here. And there is a homotopy from this lobe to this, just because this lobe is null homotopic in the complement to the other components. So we are looking at type 1 invariants. Actually, if there are any self-intersections here, even with the other components, it doesn't matter. This invariant is not going to change. Well, actually, yes, the only type 1 invariant is the linking number, so it's not an interesting thing to do. The interesting thing to do would be if we had this Kirk-Livingston finite type invariance. And then it would matter that we don't intersect the other components. But anyhow, our invariant doesn't change under this homotopy. So V bar of X is the same as V bar of X prime, where X prime has this small loop instead of the big loop. And also this is the same as V of L minus V of L prime. But I claim that this V bar of X prime is 0. And this is the so-called one-term relation, or framing independence relation. And so why is this? V bar, so I have this fragment in my picture. I don't know what happens here, but here I just have a very small loop, nothing is inside of it. I can resolve it in two ways, and I get these two pictures. I get this picture, and I get this picture. But these two pictures are the same. You can do an ambient isotopy between these two pictures, and so it's really the same singular link. Well, it's not singular, it's the same link. So the case n equals 1 is done, but it was not very interesting somehow. So to continue for n equals 2 and further cases, we first consider the following lemma, which is a generalization of this one-term relation. So if L and L prime okay. Yes, so if L is a singular link which has all its double points inside of a three-ball B such that L inverse of B is an arc. Then all finite type invariants that are well defined up to PL isotopy well, I think I should add here that, and yes, I can do it like this. So I need to assume that L has at least one double point. So I'm saying that L is not an embedded link, it's really a singular link. Well, then all finite type invariants that are well defined up to PL isotopy vanish on L. Let us prove this by induction. So we have some picture, maybe very complicated. And there is one double point, and then there is a ball such that all this complicated picture is contained inside a ball. And then also something happens outside of this ball. But the double point is inside of the ball whose preimage is an arc. Well, how do we evaluate our invariant on this singular link? We have to consider two resolutions. But these two resolutions, each of them has a local node. Each of them is an embedded link, but with a local node. So one of them will be like this. It can be called K, and another is the opposite. So K is this node, and maybe I can also denote the remaining part of this link L prime. So how about this? V bar of L is by the definition V bar of L plus minus V bar of L minus, where these are the two resolutions. Now L plus is L prime, the connected sum of L prime and some node K, this one. And L minus is L prime connected sum with another node K prime. If I change this crossing, this will be another node K prime. but this must be 0, because now these links are embedded, so actually this is not V bar but just V. And V is well defined up to PL isotopy. So we can add local nodes as many times as we wish, and it will not change the value of V. So this proves the lemma for the case of one double point. Now if you have two double points, then again you can consider there two resolutions of one of these double points. And again you have this formula with V bar, but we can now use the previous case of this lemma for singular links with one double point. And by this previous case, this will be equal to 0 and this will be equal to 0. So both of them are actually equal to 0. Because this is a singular link with one double point, and the preimage of this ball is an arc. And you can continue in the same way, and the lemma is proved. Okay, Петр Михайлович?
Да не, ну нормально, да. Просто мне вот это вот понятие, ну в принципе нет. Тут у вас написано, что связано, по модулю связаны суммы с узлом, а там у вас написано немножко другое.
Well defined up to PL isotopy, the same.
Ну, перизотопия и связанные суммы с узлом это то же самое, да? Ну ладно. Этот узел должен быть маленький.
Да. Okay, so we have this lemma.
Ну вот, я вроде понял, а вы еще говорили, что вы что-то хотите алгебраическое рассказывать.
Yes, but I have to finish the proof of the theorem. This was lemma.
Так, разве не доказана теорема?
No. No. In the theorem we have n quasi-isotopy.
Ну вот ваши эти самые шары.
No, this is not strong n quasi-isotopy, and even if we had strong n quasi-isotopy, it is not the same, because this ball intersects our link in just an arc. For a strong n quasi-embedding, we don't have this. We have a family of balls. It's a more complicated picture. But yes, so let us consider the case f equals 2. So actually, what was the definition of n quasi-embedding? So we have our double point x, which is f of p and f of q. And we have p0, which is p0. And then we must have an arc at J0 such that J0 contains the preimage of P0. And this is the points PQ. So J0 is any arc which contains the 2 points P and Q. So in the picture this can be J0. Then we have the polyhedron P1, which contains P0 union with f of J0. Well, f is the same as L. Let me call it f. And moreover, this inclusion is non-homotopic. This was one quasi-isotopy. So this null homotopy is actually contained inside of the polyhedron P1. And this Brown homotopy, which we constructed from this big loop to the small loop, is also contained inside of P1. Or, well, okay, we can assume that all these polyhedra Pi are three-dimensional manifolds, because if they are not three-dimensional manifolds, we can take their small neighborhoods and everything will be preserved. So if they are manifolds, then this loop can be taken to be inside of P1. And yes, so what can happen in this homotopy is that there can be some intersections between this homotopy and parts of our component. It cannot intersect other components, but it can intersect the same component maybe several times. Okay, then we must have the arc J1, which contains the preimage of P1. So it must contain these 2 points. It must be some bigger arc, like this, for example. And also it must contain this green arc. And then we have P2, which contains P1 and the image of J1, and also this inclusion is null homotopic.
Простите, правда ли, что в прошлый раз мы не пользовались тем, что P1 не пересекается с другими компонентами? То есть, если мы сквозь них проходили, то получались бы вторые пересечения, а наш вариант на них 0.
What do you mean last time? In the case n equals 1? Yes, we didn't use it. We didn't use it, and this is because this is a weak form of the theorem. There is a stronger form of the theorem which actually uses it, and I will mention it later. Okay, and I think this is all. Well, we also have J2, which contains the preimage of P2, and it is an arc. So this just means that P2 is destroyed from the other component. So the union of this null homotopy, which is essentially P1, so you can think of this P1 as this null homotopy. It's really the meaning of P1 is this. So you look at the image, this image of this null homotopy, and you add to it this arc, because this null homotopy intersects the link, and you have to add some arc containing these intersections. And the union of this image of the null homotopy and this arc is again null homotopic in some bigger polyhedron, which is still disjoint from the other components. Okay, now we are interested in type 2 environments. Here we had our embedded links and our original invariant. Now we consider this self-intersection, and then the difference of our invariant on these links equals the value of the extended invariant on this singular link with one double point. So this was called X, and I think it was written that this V of L minus V of L prime equals V bar of X. But then we had X prime, which is the modified version of X, which has just small loop instead of this big loop. And then V bar of X minus V bar of X prime will be the sum. So here we have several double points, and we have the homotopy from this big loop to this small loop. And each time when it intersects the link, we have a jump of our invariant. So this difference is the sum of these jumps. And each jump is the value of our invariant on the singular link with two double points. So this is the sum of the values of V bar on the links maybe X I. So X in this picture, X1 is this link which happens inside of this homotopy and has this double point, and X2 is this link which also happens in this homotopy and has this double point, and both of them also have this double point. Okay. So we are interested, we want to compute the sum of these jumps. But now X1 and X2, they are still contained in this polyhedron P1. Or maybe if these are maps, then I should write the images of these maps, but this is what I mean here. They are still contained in P1, and P1 is null homotopic in P2. So we can take, it's not quite true that X1 and X2 lie in P1, because they also contain this part which doesn't lie in P1. So I think I should write maybe I should use some notation like W1 for my component minus J1 minus J0, maybe J0. No, J. P1. Okay, J0. And then here I can write X1 minus, well, it really has to be a map. So X1 of MS1 minus W0, and also X2 of MS1. No, this has to be okay. I think I can just write x1 of j0 and x2 of j0. So this is not right. So I have this lobe, and its image, yes, is contained there. But in P1. But if I look at P2, well, this union here, it actually contains more. It contains xi of j1, not just xi of j0. Let me write here xi. But xi of j1, because the additional parts which is not in j0, they lie in this part. They are not moving in this homotopy. I mean this orange arc, which is not contained in the part of the orange arc which is not contained in the green arc. But this part is contained here, so this image is contained in this union, and this union is non-homotopic in P2. So this thing is non-homotopic in P2. So it means that this picture, including, so for example, this x1, this graph actually, this graph is null homotopic inside of P2. And I can take this null homotopy, I can assume that it shrinks everything to this point, and then I can modify this null homotopy so that I don't get just to this point, but I get to a small neighborhood of this point, and this double point is preserved like it is here. So I want to have a generic homotopy which just pushes everything into a small neighborhood of this point. And in this neighborhood I will have this picture with two double points. One double point is this, and another double point is it comes from this one. But the important thing is that now we have this small ball. This small ball is here, very small ball, which intersects the image of our singular link. Well, its pre-image is an arc. Now, so in the end of this homotopy, by this lemma, I will have the zero value of this invariant. So for each xi, I can write that v bar of xi is v bar of xi prime, which is inside of this ball, plus a sum, like this sum, because we will intersect some additional strands when we do this homotopy, and this will be a third double point. But we have a type 2 invariant, so it doesn't jump when we intersect. Our singular link already has two double points. So when we do some additional homotopy, it doesn't fill any further intersections. And our invariant doesn't jump under this homotopy. And in the end, it is zero by this lemma. So for type 2 invariants, this is the proof. But it was not clear, probably. Not clear?
Я буду задавать кучу вопросов. Первый вопрос. Правильно я понял, что вот В общем, я много не понял, поэтому, может быть, вопрос совсем о том, о чем мы говорили, но это выяснится. Вот, правда ли, что когда вот есть у нас, значит, изначальное самопересечение, есть те, которые по пути стягивания. Ну вот если стягивать J0, ну образ J0, а вот все остальное на месте. Вот в ходе этого стягивания возникают вторые самопересечения. Вот в такой момент, когда два самопересечения, наш вариант второго порядка будет.
Yes, type 2 invariant. So type 1 invariants do not jump when we make this homotopy, the original homotopy. And type 2 invariants jump. But this was the homotopy given by this null homotopy. So for the homotopy given by this null homotopy, type 1 invariants don't jump and type 2 invariants jump. But for a second homotopy given by this null homotopy, type 2 invariants don't jump and type 3 invariants can't jump. And so far we have type 2 invariants.
А как вообще может меняться вариант второго порядка, и если у нас в начале было то же, что и в конце, то есть 0, а посередине все время прибавлялось...
Посередине ничего не менялось, потому что инвариант второго порядка при этой гомотопии...
Но вот если взять вот первую гомотопию...
Yes, if we take the first homotopy, then type 2 invariant jumps, and we take into account this jump. This is exactly what is written here. So we compute our invariant. We are interested in this difference. We reduced it to the value of our invariant on the singular link with one double point, this double point. This is x. Now we have x prime, which has a small loop. Their difference is the sum of these jumps, exactly which you mentioned. Yes, so in general this can be non-zero jumps. But this was using just the hypothesis of one quasi-isotopy. This was valid for any one quasi-embedding. And now we are using the additional hypothesis from two quasi-embeddings.
Я вот вне зависимости от того, что здесь работает, хочется сказать, что не работает, я спрашиваю, будет ли в итоге верен факт, что вот те, значит, в общем, что даже если мы воспользуемся вот первой гомотопией, простейшей, то скачков на самом деле не будет.
Well, if we use this homotopy, we don't know. The jumps can be, but under some additional hypothesis, they can turn out to be zero.
Вот вопрос, как они вообще могут быть, если, ну, насколько я понимаю, инвариант второго порядка на всех зацеплениях с двумя пересечениями одинаков, потому что они преобразуются друг друга через с не менее чем тремя. Это ведь, ну, по крайней мере, когда пересекаются.
Yes, but x has one double point. So.
Да, но я имею в виду вот рассмотрим момент скачка. Мы в этот момент проходим через зацепление с двумя самопересечениями. На всех таких зацеплениях инвариант одинаков.
Yes, but it can be non-zero. It's the same, but it can be non-zero.
Значит, не нулевой, какая-то константа. Вот мы воспользовались простой гомотопией, которая левая, которая не подходит. У нас несколько раз прибавилась вот эта константа. Но у нас в результате теоремы...
This can be different constants because the combinatorics of these double points can be different.
Нам придется вычитаться.
So there is something called chord diagram. So we can have these 2 points glued together, mapped to the same point, and these 2. So the picture is like this. But we can also have a different picture. We can have these 2 points mapped to the same point, and these 2 points mapped to the same point. So the picture will be, what will be the picture? This is one, and this is another one. Okay. So type two invariant can assume different values on such two links, such two singular links, because they have different combinatorics. They are not homotopic to each other. So yes, if we don't know this condition, then these jumps can be non-zero. Each of them is in some sense a constant, but it can be non-zero.
Тогда следующий вопрос. Вот вы превратили все в такую картинку. Вопрос, что находится внутри шара? Вот и оранжевого.
Inside of the ball we have maybe I should draw a more clear picture. Where can I do it?
Ну, мне линия не нужна. Может быть, саму эту картинку стереть, она же простая очень и большая.
I don't know how good picture I can draw. I want to draw something very similar to this. Inside of it's difficult for me to draw a good picture. Sorry.
Ну а вот словами можно перечислить?
Yes. In the previous picture we had this big lobe and I replaced it by a small standard loop. It is completely standard. It lies in a small ball which intersects it like this. Now I have two double points. Apart from this double point, I have an extra double point. And I want to draw a standard picture which also has two double points, and they have the same combinatorics as these two double points in this sense. And they are contained inside of the ball.
То есть мы вот все-таки делаем некоторую гомотопию, и в момент каждого второго самопересечения отдельно применяем левую.
No. At each intersection, when we have three double points, we just use that we have type 2 invariant, and it doesn't jump when we have three double points.
Откуда три двойные точки?
Because we already have these two double points, and now we are shifting this singular link with two double points. It may still intersect additional pieces, but then this will be the third double point, and we have a type 2 environment. And in the end, when we get into this ball, we apply this lemma to this small ball. And in this small ball, we must have a picture which is combinatorially the same as our picture. And it doesn't really matter exactly how it looks like, it just needs to have the same combinatorics in this sense.
Так, ну вот у нас на этой окружности, значит, есть G0, которая раньше стягивалась, есть G1, которая, значит, вместе с P1 теперь стягивается. Вот можно как-то вот на картинке просто окружности с двумя дугами изобразить, вот что из этого попадет в шар. Хотя, наверное, я не с того начинаю, я еще не понял, каким образом стягивание внутри по 2 используется, чтобы построить какую-то монотопию.
Well, we don't actually have to be very careful about this homotopia. We just take, so we have this arc J1 whose image contains both double points, and for this image of J1 we have to keep these two double points. So we do a homotopy of this graph of this image, and then we have some tail which lies in J2, but doesn't lie in J1, and we just drag this tail somehow. We don't really care how it moves, because if it intersects something, we don't care. We have a type 2 invariant. And so what we want to have is just a combinatorially same picture, but with the same, which is inside a ball.
То есть получается, мы все-таки снаружи применяем вот гомотопию, вот простую гомотопию только G0. И в каждый момент появления второго пересечения мы вот вместе со вторым пересечением уже G1 почти стягиваем по более сложной.
Yes. I agree that this is not very. What I'm saying is not very careful. It should be presented in a better way. Sorry about this.
Сейчас непонятно, зачем здесь тогда вообще условия про то, что что-то в P2 стягиваемо, потому что, ну, это вообще какой-то парадокс. Вот предположим, у нас вариант любого конечного порядка, тогда просто вот будем будем вот так, значит, сделаем гомотопию. В момент каждого второго в своем пересечении вот зафиксируем то, что получилось, будем уже... Все, я понял.
Well, the idea is that we have n of this polyhedra if we have n quasi-isotopy. Each of them gives us an additional homotopy. Essentially, we are constructing here a multi-parameter homotopy. Like this was a homotopy from this green one to this brown one. But here we essentially have a two-parameter homotopy. We don't need it. We need one-parameter homotopy of this graph, but it is possible to construct a two-parameter homotopy. And so on. In the next step, we will have a three-parameter homotopy. And
здесь мы пользуемся только тем, что по ходу вот этих гомотопий компоненты будут пересекаться только с собой, благодаря чему все можно превратиться в эту картинку, а тем, что...
Yes, you're right.
То есть, может, получается... Я пытаюсь понять, зачем вообще пользоваться тем, что стягивание там PI в объединении с F от этой дуги есть в следующем многограннике, а не вообще. Понятно, ну чтобы следующее пересечение было с той же компонентой, да, все понял. Больше вопросов нет.
I was going to write a more detailed text, but I didn't have enough time for this. So I hope in the next few days I will make the proof in the text more detailed, and then I can send you the text. Or I don't know if it is a good idea to discuss this again next time in more detail. I agree that this is not completely. It is like an idea of proof and not the details of the proof. But maybe I'm afraid we have to leave it in this form for today. So this is an idea, and the details. Some of it is written up, but it needs to be more detailed. I agree with this. Well, maybe, yes, so any other questions about this proof? So let me just tell you how to improve this theorem. Yes, so maybe I should mention that theorems 1 and 2 are what was announced in the beginning of the talk, and then we prove the theorem which was announced in the beginning of the talk, that Rolfson problem. Yes, let me state what we proved. So we proved the following corollary to theorems 1 and 2. So if finite type invariance well defined up to PL isotopy separate PL isotopy classes of links and then isotopic PL links are PL isotopic.
Это предположение, оно получается еще более сильное, чем известное предположение о том, что инварианты конечного порядка в совокупности полны.
Yes, this is slightly stronger, yes. But eventually I'm going to replace this by a weaker and better known assumption, but this requires extra work. So the proof of this corollary is that we have these implications PL. Okay, so two given links L and L prime are PL isotopic. Then they are isotopic, obviously. Then by theorem 1 they are n quasi-isotopic for all n, and then by theorem 2 these two links are not separated by finite type invariance, well defined up to PL isotopy. And now by our hypothesis here we have this arrow, but then this arrow follows because we just go from here by this, by theorem 1, by theorem 2, and then by this assumption, and we prove this arrow. Well, maybe it's better for me to stop now, because Piotr Mikhailovich was tired, and maybe I just continue next time. And so next time I explain how to improve this theorem. So here it is needed just in the way it was proved, or at least there was the idea of proof. So any other questions? So Andreas, I have seen your email, but I didn't read it carefully yet.
Okay, I can understand this. It's too long.
Yeah, I hope I can reply maybe tomorrow. I will see. All right, then let us finish for today.
Ой, есть вопрос.
Ага, окей.
Вы с самого начала говорили, что важно будет, что речь о зацеплениях в трехмерной сфере. Где это было важно?
Aha. Aha. Yes, it is important that we consider links in the three sphere, and it is important here. So this arrow, which we somehow assume, well, I think it's still reasonable to believe in this arrow in the three sphere. But if you want this arrow to hold in arbitrary three manifolds, then this is definitely false. So let us consider the Whitehead manifold, for example. So a contractible open three manifold, which is not R3. So should I? Okay, let us assume that it exists. So there is such a fact that every such manifold contains a node which is not contained in any ball in this manifold. I think it was originally a theorem of Bing, and then there are some versions of it. I'm not sure exactly what is needed here, but anyway, it's a version of a theorem of Bing. So this node, because this node is not contained in any ball, it is not going to be PL isotopic to the unknode. This is not obvious, but it can be proved. It is a lemma proved by Smith. Smith, I don't know, Smith. So this node is not going to be PL isotopic to the unknode. Of course, the unknode is a trivial node contained in a small ball, and this one is not contained in any ball. Well, PL isotopia is can be understood as addition of local nodes, but each local node is inside of a small ball, and this unknode is inside of a small ball. And if you do a PL isotopia, you can show that at each moment your node remains inside of some ball, and this one is not inside of any ball. It is not a proof, but an idea of proof. But on the other hand, because this Whitehead manifold is contractible, of course there is a homotopy from K to the unknode. And in this homotopy there are some double points. But then you can consider some loop. So let's look at any double point. Let's look at any of these two loops. And this loop is again null homotopic in this Whitehead manifold. And in this null homotopia, there will be some double points, and you can draw a link with two double points, and then again some loop here will be null homotopic, and so on. And in this way you can show that all finite type invariants vanish on this node. And in fact it can prove that this node is n quasi-isotopic to the node for all n by the same type of considerations. So in this definition we need null homotopies inside of some polyhedra. And I think we can basically take as such polyhedra almost the entire Whitehead manifold. We just need some small piece which is not in this polyhedra, because we want to have arcs, not the entire circle. So it's not hard. Well, anyhow, so it's written up somewhere, but it's I cannot present the details now. But it can be shown that even for nodes for one component links, this conjecture fails in such manifolds. So if you ask about the usual conjecture that finite type invariants separate links without any PL isotopy, just ambient isotopy and usual finite type invariants, this conjecture also fails in such manifolds, and it's a theorem of Eisenman from around 2002 maybe. But he has an additional condition that he needs this manifold to be embeddable into R3. In my case, with PL isotopy, I don't need this condition, and he needs this condition. Maybe actually I don't understand why he needs this. Maybe it's not really necessary. But anyway, this is what he proved.